So welcome to the second session on studying about the machine language programming and studying about instruction set architecture of the processor. So in yesterday's session, we have studied that to write any assembly language program, we should know instruction set architecture of the processor. So instruction set architecture of the processor means what are the different addressing modes supported by the processor? What are the different registers present inside the processors? How the assembly language instructions are provided to link to the stack, to subroutine, to the IOs. So all this put together, we call as an instruction set architecture. Only if we are aware about the instruction set architecture of a processor, we can write an ALP code. Unlike in high-level languages, we can start writing the code with the constructs. But in ALP programming, unless we are aware of instruction set architecture of a given processor, we cannot start writing the ALP code. So yesterday we've gone through one address, two address, three address instructions, then addressing modes of the instructions, then how the different ways the memory is interfaced, the big Indian format, the little Indian format we studied. So, and also we have written two ALP programs, one for starting the adding set of numbers, other is adding set of records. So today we will just go in detail about the support provided by the ALP for using the stack, for calling the subroutines, and also for accessing the IO. So now let's understand those concepts. Before we start learning about further steps, so we will understand some concept about the instructions with the different addressing modes. This we have studied. We'll solve one or two problems related to this, and then we'll continue the discussion. Okay. So let's understand, whenever we write a programming, assembly language program, there are two styles of writing the program is there. One is called RISC style programming, reduced instruction set computing architecture programming. Most of the ARM processor use that style of programming. Other is the Intel style of writing programming for CISC architecture. So complex instruction set architecture model. So the industry, whenever the people talk about processor design, these are the two models are available. One is a RISC, other is a CISC architecture. So sometimes when you want to write a program, we may give the question, write the program with the RISC architecture keeping in mind. So we should know that what is the basic difference between the RISC and the CISC architecture. In a RISC architecture, all the arithmetic operations, arithmetic and logical operations can be performed only on the register operands. That means that whenever you write any arithmetic or logical instruction, look at the operands, source and the destination, both will be registers only. That means that all the data required to perform the operations must be present inside the processor. Whereas in case of CISC architecture like an Intel, you may have one operand inside the processor, you may have other operand outside the processor, that is in the memory. I can specify both in the instructions. So let's take one example and differentiate how does it work and then solve this question. Now, so in case of an Intel, I can write an instruction like this. I can have one register, it can be any register, it can be AX, R0 or some register, I'll use it. Another can be a memory location. So, or indirect also can use it. Add, so I can just say R0, another is a R1 like that. In a sense, one of the operand is what? Inside the CPU, inside the processor. Other operand in both the cases or what? The memory locations. So this is supported in the CISC architecture processor like an Intel processors. But whereas if you look at the instruction like this R0, R1, R2, here this is called RISC type of writing the programs. Here the source is inside the processor. Destination is also inside the processor. So that means that, so whenever you want to perform any arithmetic or logical operations in the RISC processor, all the data must be available inside the processor, then only you can perform it. You cannot have a memory operand. Whereas in CISC style, they support both the register and the memory operand as a part of the instruction. So as we know that when we write a program in CISC architecture, it is very easy to implement complex algorithm with a small set of codes. Because why? You don't require to bring it to the processor. You can directly handle the memory. So that's why. So the Intel and other processor, so their assembly code is very intact, in the sense a few lines of code is sufficient to implement a bigger algorithm in a high-level language. Whereas here, you require a lot of instructions required to implement even a small algorithms, because all the data should be there inside the processor. But still, the purpose is different. RISC is used to manufacture controllers and processors which are used in embedded market, whereas Intel manufacture the processors which are used in higher performance missions, data centers. So which is computers are used in higher computational purposes. So now in this question, the concept is being used. Let's read this question and understand the meaning and how we have solved it. So give a short sequence of mission instructions for the task. Add the contents of memory location A to those of location B and place the answer in location C. Simple. A plus B and answer to be kept in the C. Instructions load, location, RI and store RI, location are the only instructions available to transfer data between the memory and the general purpose register. Do not destroy the contents of either location A or B. Assuming the instruction formats given in the question and a RISC type processor. So what does it mean? That I have to add the contents of A plus B and I have to store the answer in C. In a normal CISC like process, I can directly write single instruction, add A, B, C. I can put it. But here in the RISC specified, I cannot access the memory operand when I perform addition. So what is it we have to do? First, we have to bring the memory contents into a processor. So that is the instruction load A, R0. That means that, so I am bringing the contents of memory location A to register called R0. So then get another operand also into the memory, from memory, load B, R1. Load the contents of B to register called R1. Always remember that load means the source will not be disturbed. Only thing, copy of that is being used to make the movement from one place to other place. Now, once you have the data available in both the registers, I can use the instruction add R0, R1, R2. So both have been added and the answer is stored in a R2. So now let's look at the last instruction. Once you have the answer, I have to keep the answer in the memory. So store R2, C. So like this, whenever we specify the RISC type, always remember that all the arithmetic instruction, whatever you perform, operand should be registered. That you have to keep it in mind. So that is why RISC type of programming is also called as load store architecture, because load and store is the only two instructions available to access the memory. No other instructions can access the memory. Only load and store can access it. You can get the data into the processor using load. You can move the data from the processor to the memory using a store instructions. Let's go to the next question. Register R1 and R2 of a computer contain the decimal values 3500 and 2800. Find the effective address of the memory operand in each of the following instructions. Now let's look at the first instruction. Store R3, 50, R1, R2. So let's understand the meaning and addressing mode here. So what is the meaning? Store. Store means, so always move from left to right. I'm moving it. Destination is always on the right side. So contents of R3 is stored in a memory location whose address is prepared by three components, 50, R1, R2. That means that contents of R1, contents of R2 plus 50, all of them added together, and whatever the value you get, that is an effective address. From there we are picking the data. So or from that is an address we are referring now to move the contents of R3. So you can just look at effective address 50 plus R1 plus R2. So R1 contents is given already. So 3500, R2 contents is given 2800, 6350 is the effective address. This is the address where the contents of R3 will be stored. Look at the next one, at minus R1, R5. So when I say minus before any of the indirect addressing mode, that means that what? It's a pre-increment. We have to decrement that by 4, and then the R1 contents has to be used as an address. So that value will be added to R5. So and again answer is stored in the R5. So this is a in this case, this is like a CISC architecture instruction, because why? Memory is also referred and the register is also referred. Let's see that now. So R1 contains 3500 minus 4, that is 3496. So before using, we have decremented by 4. Why 4? Because it's a one word 32-bit number is stored in the memory. It requires 4 addresses to store one 32-bit number. That is why when we say decrement by 4 for 32-bit machine. So the 3496 is an address. Assume the word length is a 32-bit. So again, the R1 contents contain the now address of the memory location. So point is decremented by 4 and is used. So that's all the case. We don't require to perform any operation here. The question is only asked to find out or compute effective address. So answer is 6350. So 3496 is the another case. Now, so we'll go to the question number 13. Question number 13. A processor has 40 distinct instructions and 24 general purpose registers. A 32-bit instruction word has an opcode, 2 register operands, and an immediate operand. Give the number of bits available for the immediate operand, immediate operand field. So let's understand for a moment the concept, and then we'll go to the answer. So here, Mohan. Hello. Hello. Mohan, is it audible?
Yes, sir. Audible, sir.
Okay.
Yes, sir.
So any instruction basically consists of set of bits. So in the question they have specified it's a 32 bits. It forms of one instruction format. So every instruction, as indicated there in the question, contains information about opcode. So operand 1, operand 2, and another operand 3. So the 3 operands the question specified. So this operand indicates one register operand. This is also another register operand, and this is the immediate operand. So now we have to calculate what is the space required for the opcode. So in the question they specified that 40 distinct instructions are there. That means that I supposed to specify the 40 instructions in the binary format, in the opcode format. So we know that 2 to the power of 5 means 32 is not possible. So 2 to the power of 6, I have to use it. So 6 bits I have to using for opcodes. So 6 bits I'll be using for the opcodes. Now, so the question also specified that there are totally 24 general purpose registers are there. Totally 24 general purpose registers are there. That means that if operand 1 is nothing but a register operand, means this register can be any register from R0 to R23. So this can be any register I can able to specify. Now bits are required to represent 24. Again 2 to the power of 4 is 16, not possible. 5 is 32. So that means that 5 bits are required. So to represent one register operand, I require 5 bits. Similarly, there is another operand they specified is a register operand, so that another 5 bits will be required for this. Now, so totally in the 32 bits now, how many we left out? So 6 plus 5 plus the 5. So that is nothing but, so 32 minus, so 11 bits are there, 11 bits. So if you look at that, 5 plus 5, 10, 16, totally 16 bits are there. So now remaining is 16 bits are available. So remaining is totally 16 bits are available. So these 16 bits now available for representing another operand, which is an immediate operand. So the instruction can be look like this. This instruction typically it can be look like this: add R1 R2 hash 50, like that instruction. This appears look like this. That means that this is an immediate operand represented by here. This is a one register operand represented by another operand. There's another register operand represented like this. There's an add which is represented like this. So this is how instructions are encoded, correct? No? Inside a 32-bit format. So this is the question they asked. So you can just read that: 2 power 6, 64, 6 bits for the opcode, 5 bits for the registers. So totally 10 bits for the two register operands. 32 minus 6 plus 16 bits is available to represent immediate operand. So questions like this you should analyze. So what is the requirement? What is supposed to do it? Now, so let's understand another instruction. Write the meaning of the following instructions and the contents of the registers R4, R2 after the execution of the following instructions are programmed. Assume following values before the execution of the program. R4 is given 5, R2 is given 6, and they have given the contents of the memory location called 5, 2. Now look at the first instruction: add R4, R2. It's direct. R4 plus R2 will be added together. Answer is saved in the R2. So it's nothing but 5 plus 6. It will be 11 in the decimal. So we have written 5 plus 6 is, so 11 the decimal, or if you are using an hexadecimal, it's a B. 0x, 0B is in hexadecimal. So now what is the second instruction? Add R4 indirect. That means that R4 contents will be acting as a pointer now. What does an R4 is referring now? So R4 is referring to the 05. So bracket of R4 means go to the location whose address is indicated by R4. So R4 they are given 5, and also in the question they are given contents of the location called 5, that is 02. So that means that whole of this operand represents a number called 2. So that will be moved into R2. So that is added with the contents of R2. So what is there in the R2? 6 is there. So 6 plus 2, 8. 8 will be stored into R2. So you can just see that, add the contents of pointed by R4, that is 5, 2. So that is a 2 value. And then the contents of R2 is 6. And the contents of R2 is, so now it's changed. The contents of R2, because of the first instruction, it has become a 11 decimal. And store the answer, then R2. Answer is 13D. So because of the first instruction, R2 contents has become 11. And because of the second instruction, 2 is added to the 11. It becomes a 13 decimal. So, or you can write in a hexadecimal also. So like this, given set of instructions, so find out the value in each of the register, destination register after each instruction, and then use that value in evaluating the next instruction. Now, so another question: prepare the machine code for the add instruction as per the information given in the following figure. So what are the information they given? They are given on format here. That means that instruction style is given here. What is the instruction style? Operation, destination operand will be the first indicated. Then the one of the source operand indicated called A. Another source operand is indicated B. So then, so answer is moved into the destination RA plus RB. So this is like a risk way of writing the program. Here I'm moving from right to left. In all the instructions till now, whatever we studied with reference to Hammershell book. Left to right. Destination is always on the right side. Now in this instruction, they are given that. So destination on the left side and the source operand is on the right side. So please take care when the question is given, what is the order in which they are given it. So now, so they specified this instruction is encoded in this particular format. So now total number of bits are used to represent this instruction is 16 bits. So first is 0th bit, the last is the 15th bit. In this, they have already indicated in the question itself, where is the space, how many bits and where is that allocated for each of the operand. For example, OP, how many bits are given? See, OP you can look at here. So O0, O1, O2, O3. That means that 4 bits has been allocated to specifying the operation. Now, similarly, destination is specified by 1, 2, 3 bits, and their place is bit number 6, 7, 8. Similarly, RA, so it's represented by RA0, 1, 2, 3 bits, and their position in the 16 bits is this position. Similarly, RB. So RB is now represented by 3 bits, and their position in the 16 bits is RB0, 1, 2. So now I've understood the encoding format and the way instruction works also. Now the question is, I have to represent this instruction called add R1, R4, R0 in this format. So let's start writing it. Now I'll take R1, R4, R6. So before start coding it, I will prepare what is the machine code for add. So since they have not given any details, we can assume, I am assuming the given instruction add, the opcode for add is 00. So I'm assuming, making one assumption, opcode for add is 00. So that means that, so 4 bits are required to represent the add. So I'll be substituting at O3, O2, O1, O0 what? 00s, because opcode for add is what? 00. That's what we have written here, 00. Now look at R1. R1 position indicates what? It's a destination. They are specified. The first operand is nothing but acting as a destination. So what is the value of that? R1. Since each of the registers are provided 3 bits, so their number starts in the binary is what? 0, 1, 2, 3, 4 up to, so 7 is there. So R1 is nothing but what? 0, 0, 1 represents R1 register. That has to be filled in what? Destination position. So now destination is what? Bit number 8, 7 and the 6. So that is, you can just look at here. We have written 0, 0, 1. Similarly, now R4. R4, what is the binary code for R4? It's a 1, 0, 0. So that has been represented where? In the position RA. So you can look at here, bit number 3, 4, 5, I substituted with 1, 0, 0. Similarly, R6. What is the binary code for R6? 3 in the 3 bits, it's 1, 1, 0. So 1, 1, 0 is represented in the bit positions 0, 1, 2. Now, after writing all the 16 bits, I have to write in hexadecimal format. So what we do, I make a group of 4 bits. So first 4 bits, 0, 1, 1, 0, I'll make one grouping. That is one grouping. Again, I'll take another next 4 bits, 0, 1, 1, 0, I'll make another nibble. Like this, 4 bits together, I'll make one nibble. After I prepare all the 4 bits, I'll represent each 4 of the bit by a nibble. For example, first one, 0, 0, 1, 0 is 2, 0, 0 is 0, 0, 1, 1, 0 is 6, then 0, 1, 1, 0 is 6. So the total value of this instruction in machine language or object code is nothing but 0x2066 or 2066H. So like that, given any instruction, given the template, it's called as an instruction template, we can always represent in a binary or a machine language format. This is what assemblers does. Assemblers, if you give a high-level language like an English statement like add, subtraction, it uses the instruction template of the processor. It converts into what? This machine language format. What assembler does, we are doing the same thing here manually. Okay. So this is some of the programs we have done based on the knowledge what we have what is the understanding we had from the yesterday's session. Okay. So today we will continue now the ALP support given for input-output devices, subroutines, and the stacks. Now, look at the processor. The processor works at the speed of megahertz to gigahertz. It works very high speed. Look at the speed at which the keyboard works. It's very slow. Look at the speed at which your displays work. It's also slow. That means that there is a speed gap between the processor and the input-output devices. Now, you cannot expect the keyboard will supply the data at the speed of the processor. You cannot expect the display will consume the data at the speed of the processor. So there should be some support should be provided in the devices, that is keyboard or the display, to support the synchronization between the processor and the input-output devices. What do you mean by synchronization? Time synchronization. One is faster, one is slow. There should be a way to synchronize both of these speeds. So let's understand the keyboard. To support slower input devices, most of the devices we provide what is called one buffer register they provide. Let's say it's an 8-bit. I assume that it's an 8-bit register. So here in this case keyboard, data in is the name of a input, the buffer register. Now, whenever you press a key and the data, whatever the ASCII code of the key pressed will be stored in the data in. Now, so how does the processor knows that there is a data is present in the keyboard? I have to read it. It does not know that. Whenever user makes a call to the keyboard, what does the program has to do it? Program has to keep checking the keyboard whether the data is there or not. For that, what they do is all the input devices, they provide what is called as flags. So what is a flag? It is called as 1-bit flip-flop. So in this case keyboard, they provided 1-bit flag called status input. So generally, there is a lot of other flags also present in the keyboard. Among that, one flag is status in. So the register which contains this bit is called as a status register. So we are assuming in this case, sample example, the bit number 3 of the status register represent what is called status in flag. So now we have understood that all the input devices will have a buffer register where the data will be kept as soon as the data is available. So processor should keep checking the status in flag to find out whether data is available or not. Whenever the flag is 1, it is an indication to the processor the data is ready. You can read the data from the data in register. So now we will do that portion here. So look at that. Move hash location R0. Here in this case, the location is an immediate addressing mode. Even though it's an immediate addressing mode, here location is not a value. Location is address of the memory location. And I'm moving that value into R0. So now R0 acts as what? A pointer which points to the memory location called location. So now test bit. Test bit is an instructions provided in assembly language. It is nothing but, it is like a AND instruction. So test bit is nothing but pseudo AND instruction. So what is this instruction will do it? It will take the bit number 3. Hash 3 means what? Bit number. It's a bit number. So the bit number 3 is ANDed with in status. In status is a status register present inside the keyboard device. In that we are interested in the bit number 1, which indicates what? The status input, whether the data in has got a data or not. So test bit is ANDing. So the bit 3 with this one. Whenever you perform AND operation, what will happen? All the bits other than the third bit becomes 0. Only the bit which you are interested will remain. So in the sense, if I do the test bit of 3 in status, the whole answer becomes what? Either 0 or 1. If the third bit is 1, the whole answer becomes what? Non-zero value. If the third bit is 0, that means that whole answer becomes what? 0. So whenever you perform a test bit, 0 flag will be affected. Now we know that after 0 flag is affected, in the next instruction I can look for the 0 flag by using branch instruction. Branch equals 0 means if the previous instruction has produced the 0 answer, go back to the read. So go back to the read means keep on reading it until what? SIN becomes 1. Whenever SIN becomes 1, then what we do? We come back to the next statement, then read the data what is present in the keyboard buffer data in and store it in the memory location pointed by the pointer R0. So this is how slower input devices are interfaced at the low level by the processor. What is a disadvantage and advantage of this method? So here you are not missing the data at any cost because you are in the loop only. You are not missing because processor runs at least 100 times, 1000 times, more than 10,000 times faster than your devices. So that there is no way you are missing the data. You always get the data. But the one problem is it blocks the processor. Processor cannot do any other job because always you are in the blocking call. So that is why to avoid the blocking, nowadays the people use what is concept called interrupts and the DMA. That means that only when I get an interrupt, my program will go and read the data from the keyboard. DMA means whenever you have a data, large set of data, you can directly transfer to the memory without the involvement of CPU. These are the new concepts what is used in the industry today. So this type of reading with a continuous checking of the flag is called as program controlled IO. So program control, under the control of program, your IO access is done. It's called program controlled IO. So now same way, how do we write the data to the processor? Once I have the data from the keyboard, it is stored in the memory. Now I want to write from the memory to the processor. So how do we do it? Whenever you write any data to the display or printer takes its own time to consume the data to print on the printer or to display on the screen. It takes its own time. That means that processor cannot start writing the new data unless previous data what is written is consumed. So the processor should know that the previous data is consumed or not. How does it know that? Again, there is a flag is present inside all the output devices. Let's say in this case called as status out. It is a 1 bit of the status register. Many flags are there. 1 bit is called as status out. So what we have to do is, so whenever the status out is 0 means still something is going on in the display. So don't write the new data. Whenever this bit becomes 1, that means that it is ready to receive the new data. So that is what it's written. Again, test bit, check for the bit number 3 in the out status. Now, whenever it becomes 0 means still it is not consumed the data, keep on repeating it. So whenever it's ready, that means that SOut is 1, move the data from the memory wherever we have stored in the previous keyboard program into the buffer register which is present inside the display or the printer. So this is how we do it. So the same program continues until new line character is pressed. That's what compare. Carriage return means hash CR means what? It's a 13. 13 is a ASCII code for a carriage return compared with a memory location. If it is not the 13 entered by the user in the keyboard, increment the pointer automatically, post increment. You can say plus after that, and then branch continues. So it keeps on doing this program. So this is how it works here. So this is a concept people use whenever input output devices has to be read in the low level code or ALP code. Now let's go to the concept called stacks. So before I just explain the stack, let's understand the concept of stack and then we will continue program. Okay, now how does the stack concept works with the processor? Now, if this is the processor, this is a processor, and the memory is connected to the processor. So whenever we use a word called stack, we know that stack, what we are talking is a process stack. That means that stack is a part of the memory. So this stack, which is part of the memory, so it has to be reserved with some what is called as the lower value and the upper value. It has to be reserved. You have to fix it. Where is the stock begins? Where is the stack end? Because why? This memory is limited. So if it is a 32-bit, 0 to the power of 32 minus 1, it's a limited. So since it's a limited, so we should know that it is always stack should be take only fixed amount of space. So I should define as a programmer what is the beginning and what is the end of the stack. Now, stack always will be recognized by what is called as top of the stack, TOS. Now, whether top of the stack is a memory location or any special provision is provided in the processor to support this one, yes, special provision is provided. It's called stack pointer. Most of the processors and all the processors requires a stack pointer to support the top of the stack. So now it is always pointing to the top of the stack. So if its stack pointer is pointing to this location, that means that all these locations are filled. So it's pointing to the top of the stack. Now, stack grows from lower address to the higher address or higher address to lower address. That depends on the process. So in most of the process, stack grows from higher address to the lower address. That means that this address is an higher address. So let's say if it's 1000, so and let's say this is the 500 is a limitation. That means that every time you push the data, stack grows from higher address to lower address. So 1000 it will be there, then 996, then 992, like that it decrements and grows to this address. So stack grows from higher address to the lower address. Now, so with these concepts, now we will implement how push operation is implemented inside the stack, how the pop operation is implemented inside the stack. Push means, of course, before we push it, we can always compare whether there is a space in the stack. If there is no space in the stack, we can always say that what? It's a full error, we can produce it. How do you find out that? We can always compare what is the top location of the stack address. So with the current value of the stack pointer, compare them, and based on that difference, you can exit saying that its stack is full. After doing that one, how do you implement the push operation? So push I can implement by what is called as move instruction. Move move instruction, I'll take some value called R0 and I'll use the stack pointer and say minus. So this is called a push operation. That means that stack pointer contents will be decremented by 4. So if the stack point is pointing to 1000, it will be decremented by 4. It becomes 996. And then at that location, the new value of R0 will be returned. So this is how push operation will be implemented. Similarly, pop. So in case of pop also, whenever you pop, you can find out is there anything is there in the stack or not. If nothing is there in the stack, you can just say that it's an empty stack is empty. So how do you find out that? Again, from the higher location, that is a bottom address, you can find out, compare with the stack pointer, and then take a decision, is it empty or not. So if it's not empty, you can pop. So how do we pop? So move SP, that it's pointing to the top of the stack, take the value and put into the whichever register you want it, and then plus after that. So in case of a pop, so the whatever the stack pointer pointing is already pointing to a place where you have some data. Take that data and then so increment the stack pointer by 4. So because why stack grows from higher address to lower address. So with this concept, now we will understand the program here. Now look at the example. Look at the example here. We have given an example. So stack pointer is pointing to this location at this moment of time. Now the value of the stack pointer is 1000. So in this left side figure, we have given existing current value of stack pointer. Now bottom is the place where the stack starts. So and stack can grow from that address. Now SP is currently now contents is 1000 and it's pointing to the top of the stack. The top of the stack value is what? Minus 28. And every word here is a 32-bit word. That's why the address is what? 0, 4, 8 like that. It's incremented. Now let's perform the push operation. After pushing the new item, then what will happen? When I say push instruction is executed, the contents of the stack pointer which was pointing to the minus 28 will be decremented by 4. So that's why SP becomes 996. Now once it decrements, there is a place is there where you can store the new value. So what was the item? 19 was the item was available. I am storing at that place. This is how the push operation will be done. So SP will be decremented by 4 and the new value will be stored in the top of the stack. Let's take the same again assumption. Stack is 1000. We will pop now. So when I say stack is 1000, when I pop, what will happen? Stack pointer will be so added by 4. So SP becomes now 1004, 1000 to 1004, and whatever the value which was there in the top of the stack minus 28 will be popped out and given as the value, that is item will becomes minus 28. Like that, stack pointer always decrements when the push operation is performed. Stack pointer always increments by 4 whenever the pop operation is performed. Now, so queues is the same concept. Okay. Now we'll go to the subroutines. Now, how does the subroutines support is provided inside the ALP language? Now, there are two special instructions are provided in the assembly language to support subroutines. So what are the two instructions? One is called call instruction, other is called as a return instruction. Most of the processor, almost all the processors provide these two instructions. One is call and this is a return. When we call branch, you go to a particular place, execute and will never come back. The difference between a call and a branch. In case of a call, you are going to a particular place, execute it and you're coming back to the same place where you are called. So what happens when a call is done? There is a special register is provided in the latest ARM architectures. That register called the link register. Now, whenever we call a subroutine, there is a two possibilities are there. There are two possibilities are there. So if this is a processor is available, if this is a processor, and if this is a memory is available here. Now, let's say call instruction is available here. If I make a call here to some subroutine which is available in the memory itself. Now, what is the provision? Generally, what we do is, so whenever we call, so the return address, this is called the return address where I have to come back. I have to execute this program, and after that, I have to come back to this place. I have to come back to here. Then what generally do people were doing earlier in architectures were, this return instruction, whatever the return address will be saved in the stack. So return address was saved in the stack. It was the return address was pushed here, return address. And then once you finish your subroutine, when you go back, we pick from the stack return address and then we were going it. The problem with this is what? The processor, for the processor, the memory is outside. The stack is outside. So every time we have to branch from a call to another subroutine. So we have to write the return address into the stack. And whenever we have to finish that, we have to pick from the stack. That means that processor outside, it has to write. Stack is outside. So you have to write into the stack always. You have to read from the stack. So more time was required because why? You're writing to a memory which is outside, not inside the processor. So then they thought that, let us, in the latest architects like ARM, they thought that why we have to store the return address inside the stack? Why can't we store inside some register? So that lead to a concept called link register. So link register is a register which is also 32-bit, which is present inside the processor. Now, when I say call is called, the address of the next instruction, who holds the address of the next instruction? Program counter. Where is a program counter? That is also inside the processor. So you don't require to go outside the processor and keep it in a memory. You can just copy the contents of the program counter into a link register. Then you branch to the subroutine, finish the execution. When we branch to the subroutine, what will happen? The new address 1000 will be loaded into the program counter, and then execution starts. All the instructions will be executed. Whenever you say return, return is an explicit instruction you have to write at the last instruction of the subroutine. Whenever I say return, again I don't require to go out of the process, because why? It's already there in the link register. So which was there in the 204. Just we copy that into the program counter and return back to here. So this concept of using the link register, which is present inside the processor itself, reduces the time required to branch from one place to the other place by using a call instruction. But what's the disadvantage of the link register? One level of calling the subroutine is okay. Again, if I call another subroutine within the subroutine, then what will happen? You have to overwrite the link register, previous value is lost. Then we have to require stack is required. So most of the Intel processor, still they use concept called stack to store the return addresses. In the latest architecture, they use what is called link register. That's why one level of nesting, it will be very faster. When you do a lot of levels of nesting, it will become a slower because you have to store the addresses in the stack. So now let us understand a little more details about how, when the stack is used to store the return addresses in a subroutine, that is when multi-level nesting is there, we have to use the stack, how it is used, but also at the same time we'll understand that how a stack is used to pass the arguments from a program to from the main program to the subroutine. So let's understand that concept now. So we will understand. So now when we call some subroutine, I have to call, let's say, some sub1, I'm calling it. So this is the sub1. So this is my code is available here written. Now, so whenever we call a subroutine, we will pass what are called arguments for the subroutine. So in C language, whatever there we pass through a parenthesis, we pass the values. But whatever you pass in the parenthesis, how exactly it is implemented in assembly language or the low level language, whatever you write in C, ultimately it has to convert into assembly. So let's learn that what are the ways you can pass the data into a subroutine. Number one, you can pass the data through a registers. That means that you can put some value into a register. Let's say move R0 hash number 1. So then, when you are in the subroutine, I know that R0 contains a number 1. I can use them in the program. That means that through registers I can pass it. Second is what? Through memory locations. That means that I can store in some memory locations in the beginning itself. Let's say move some location 1, some data, I have it, some data, say let's say num2. Now what I'll do is inside the subroutine, I know that location 1 contains some data. I can access that into another register. I can use it. This is another method. This is called global variables. This is passing by value. Now there's another method called as passing through stack. Now, so what we do is between the subroutine and between the main program, so we use a stack as a space. So now what we do is before I call the subroutine, I will push all my arguments into the stack, push it, and then in the subroutine, I'll access all the data into the subroutine. So this method of using the stack for passing the arguments is extensively used to implement pass by reference, also pass by value. So we push all the values here and then we will be able to access it here. Now we will see that with an example. So now in this program, the sample program, what we have written here. So I am passing one value NR1. N means name of the memory location. So which contains the number of numbers. Let's say we are written a subroutine to add the set of numbers. This is the subroutine job, is to add the set of numbers. Now, whenever I call the subroutine which can add the set of numbers, two things I have to pass. One is how many numbers I supposed to add it, which I have stored in a memory location. I put it into the R1. So this is like a global variable, and there's a n memory locations there. From there, I am putting into R1. Now, since R1 is accessible inside the subroutine, so it is also, you can call as a pass by value. Now, hash num1. Num1 is what? It's a pointer. It is referring to the numbers where we are stored in the memory. So when I say hash num1, num1 is what here? In this case, it's an address where all the numbers are stored. I am passing this address into the R2. Now, R2, R1, both are being passed to the subroutine called list addition, but one contains the value, other contains a pointer. So we should remember that one contains the value, other contains the pointer. So now when I say call list addition, it comes to this program here. Now I can access the values called R1 and R2, which has been passed to here. So I'll do the logic here, and then once I finish my program, I can always go back to the main program. When I go back to the main program, I can keep the answer in one of the registers and go back. So then what I'm doing, once I come back here, I know that answer is there in the R0. I'm keeping the answer to a memory location called sum. So like this, so you can pass the number by value or by reference into the subroutine and access them inside the subroutine. So now we will understand the concept called as stack frame. So in this program, what we have done is generally how typically a stack is used for passing the arguments, and also how stack is used to store the return address. So here we are not using the link register concept. We are using the stack for storing both the return address, and also stack is used to pass the arguments to the program, and also stack is used to return the data from the stack to the main program. So let's observe carefully what is we have done here. Now, before I call the subroutine, before I use the subroutine, I am assuming level 1 is the place where stack point is pointing. So before the subroutine initiation starts, the stack point is pointing to what is called as level 1. So now it's pointing to somewhere called level 1. Now I start using the stack for implementing the subroutine call. What all the things we do it? So whatever the arguments which are required for the subroutine, you have to put into the stack. In the previous slide, I've used, you can, if you just look at the previous slide, we have used the registers to pass the data to a stack. In this case, I'm using what? Stack is used to pass the arguments. In the previous case, I pass the data to a subroutine to the registers. Now in this case, I'm using a stack to pass the arguments, to store the return address, and also to return the result. Everything stack is used. This is how most of the compilers implement the procedure calls. Now, so what are the two arguments which are required for the subroutine? The one is a pointer where the numbers are stored. I am pushing into the stack. This is a push instruction. Move the number, that is an address, comma minus SP. That's like a push instruction. The moment I say push, what will happen? Stack pointer will be decremented by 4 and the num1 value will be saved. Now look at the stack pointer picture. So level 1 which was there, now it's decremented by 4, num1 will be saved. Now I also push how many numbers I supposed to add it. Move n to the minus SP. This is another push instruction. Again SP will be decremented by 4 and the n will be saved. Now I'll initiate the call instruction. The moment I say call list address, what will happen? The return address means what? The address of the add instruction has to be saved into the stack, because we are using the stack for storing the return address. So now look at that. Return address is nothing but address of the add instruction will be saved here. Now again stack pointer was decremented and return address will be saved. Now already stack, what is the level 1? Before you go to the subroutine, stack now is at what level? It's a level 2. What all there in the stack? arguments which has been passed to the subroutine from the main program plus the return address. So 4 plus 4 plus 4. So 12 bytes have been stored into the stack top. So it is now at the level 2. Now once you start executing any of the subroutine, always we have this challenge, because when you are writing the main program, you would have used the registers, all the registers present inside the processor to do some other algorithm. Now, the moment you call the list address, you come to the same place, you come to the place where again you require registers to implement some other logics. But I cannot start using the registers directly, because why? Whatever there in the register, first I have to store it someplace, then use the registers. When I finish it, when I go back to the main program, restore all the values what was present in the registers and then go back. So that is why generally in the beginning of any subroutine, the programmers will write the contents of the existing values of the registers and put into the stack. Move multiple is nothing but like a move instruction, but these instructions supported by the ARM, they provide multiple registers can be written simultaneously with a single instruction into the processor. So when I say move R0, R1, R2 means I'm writing the contents of R0, R1, R2 into the stack. How many push? It's equivalent to 3 pushes. First, I'll push the R0, decrement the stack pointer and store R0. Then again decrement the stack pointer and store R1. Again decrement the stack pointer and store the value of R2. Now the stack pointer is pointing to wait level 3. Now once you save this one, then I'll finish all my program logics. How do I finish my all logics? First of all, I should be able to fetch the data which has been passed to the subroutine. That is nothing but arguments. What are the 2 arguments we have passed? Num1 is one argument I have passed, and n is another argument I have passed. Which is that on the top, n is available on the top, then the below that num1 is available. Now n is available at a place 16 bytes from the stack pointer. You can just count it. 4, 4, 4, 4, 16. That means that when I say 16 stack pointer means stack pointer contents plus 16, if I add it, it will go to a memory location address where n is stored. Now get that value into R1. So similarly, get the value of num1 into R2. So once you receive the value argument which has been passed from a main program to the subroutine, that is R1, R2, then implement all my logic what is required to find out the sum of all the numbers. Once you finish the program, then what is the procedure? You have to keep on popping the values in the same order. So first of all, get back R2, R1, R0 into the registers. So old values. So move multiple SP plus. See that it's a pop operation. That is why first take the value and then increment the stack pointer. Take the value and then increment the stack pointer. Like this, 3 times pop operation is done by the move multiple, and all the R2, R1, R0 is popped out, and it has stack pointer is now pointed to what? Level 2. Now, when you are there in the level 2, I say return instruction. The moment return means what will happen? Whatever the return address stored in the top of the stack, on the top of the stack, whatever there, it considers what return address, it will be popped from the subroutine, so from the stack, and that value will be loaded into the program counter, so that you go back to the place wherever the instruction was, which was the instruction which was there after the call. So now the return address is popped. Now stack point is pointing to what? The place where n is stored. Now I have to get back that value. Either, if at all, if you are passing the answer in the same memory location wherever you pass an argument. Now stack point is pointing to what? N. The same place we could have used to pass the answer. In such cases, what we do? Before this statement, I can read the contents of the memory location in the stack, which is pointed by the top of the, which is nothing but pointed by the stack pointer, and then so I can always adjust the stack pointer. Now, how do you adjust the stack pointer? Add 8 to the stack pointer, so the stack pointer go to the level 1. So like this, we can always use the stack to do 3 jobs. Number 1, pass the arguments, store the return address, then again store the answer, and then go back to the main program, pass the answer. Every time you have to make sure that once you finish your subroutine, wherever stack top was there, same location we have to set the stack pointer. So if you do any mistake here, then what will happen? Stack overflow occurs. So this concept of passing the set of arguments, return address, and the whole what is called the set of locations which are being prepared on the top of the stack is called as stack frame for that subroutine. So we can say that during execution of a subroutine, 6 locations at the top of the stack contain entries that are needed by the subroutine. These locations constitute private workspace for the subroutine, created at the time of the subroutine is entered and freed up when the subroutine returns control to the calling program. So such a space is called as stack frame. So if the subroutine requires more space for local memory variables, they can also be allocated on the stack. That means that after storing R0, R1, R2, you can also use the area for storing other local variables. So this is called as stack frame, the concept called stack frame. So there is another concept called as frame pointer is available. So what is the purpose of frame pointer? So whenever we implement nesting of the subroutine, that is one subroutine, one call I'm making to the first subroutine, again the first subroutine making a call to the second subroutine. Like that, whenever you make nesting of the subroutines, so then what will happen? Many stack frames will be created. So you can just see that this is a stack frame of the first subroutine. This is a stack frame of the second subroutine. Then what will happen? Stack pointer keeps moving. So stack pointer will be keep changing every time the new data or the local variables or the return address is stored. It's keep changing. So whenever you are in any of the subroutine, either in the first subroutine, the second subroutine, if I want to access the data, that means that access the argument passed from the main program to the subroutine, there should be a unique way of accessing it. I should know that. If I, with reference to stack pointer, if I go 8 locations, if I add 8, I should get the first argument. If I add, let's say 12, I should get the second argument. If that reference is there, it is easy for the programmer who is writing any subroutine, that is with reference to stack pointer, if I add this much, I get the first argument like that. Now it's not possible because you're using the stack for what? Storing the local variables, storing the registers, return address, so many things you're using the stack, because stack is required for the programmer to implement different logics for in each subroutine. To make it easier for the programmer to access the arguments passed to the subroutine, they use what is called as frame pointer. So what is a frame pointer? So this is the generic stack frame. So any number of parameters before calling the subroutine, we know that arguments pass from the main program to the subroutine. Here in this case, we assumed 4 parameters have been pushed to the stack, and then the subroutine is called, return address is saved. There is a separate register called frame pointer, which is called as an alternate stack pointer. Generally, there is no separate specific register called FP is available in the processor. Any one of the registers what is available can be used as a frame pointer in some of the process. So whenever the frame pointer is there, what does it mean? That as soon as the control goes from the main program to the subroutine, immediately we'll copy the value of the stack pointer into the frame pointer and use the frame pointer to access all the arguments what is there in the stack frame for that subroutine. So what will happen? Otherwise, if there is no frame pointer is available, let's say what will happen? Then what will happen? The moment you go to the subroutine, you make the stack pointer to grow, stack pointer to decrease and keep pushing a lot of data into the stack. You put the registers, you put some temporary variables, everything. What will happen? You don't know where is the stack pointer address, and you don't know from stack pointer how far is your arguments are there, because it keeps changing. It's a very challenging for the programmer to calculate the offset value from the stack pointer for your first argument, the second argument. So instead of that, what we do, take one register called as alternate stack pointer FP. As soon as you enter into the subroutine, copy the value of the stack pointer to the frame pointer. Don't change the frame pointer. Now it's a fixed set. Now allow the stack to grow as you want. Stack pointer, let it change, but nothing happens because I have an alternate stack pointer called frame pointer. With reference to that, I will access all the arguments. So this is the concept as being used to access all the arguments what is there in the stack frame. Now look at the here. So since you are using a frame pointer, one change is there. I push all the arguments into the stack. The moment call is executed, return address will be saved. Now frame pointer is another register. Some contents will be there in the frame pointer. I cannot start using the frame pointer immediately. First of all, what is there in the frame pointer? I have to save into the stack and then start using it. This is one instruction is always required whenever the frame pointer is used. So I'll push the contents of the frame pointer into the stack, and then once I push it, then this is the place where the frame pointer is pointed. It will never change. For every subroutine, frame pointer is always pointing to this place. Now, Now, once you copy the contents of stack pointer to the frame pointer is fixed at this point. Now the stack pointer can grow. Stack pointer can keep changing. Now after that, what you create some local variables for the subroutine. You use the stack for keeping some local variables. You save some of the register contents in the stack. This stack pointers keep growing. But look at the frame point. It's a fixed at this place for every subroutine at whatever the level of nesting. It's always fixed at this portion. Now you can calculate how far is the parameter 1. So if I say frame pointer plus 8, I'll always get the parameter 1. Frame pointer 12, I'll get a parameter 2. So plus 16, parameter 3. So plus 20, parameter 4. That means that with reference to frame pointer, always fixed offset, I know that parameter 1, 2, 3, 4 is there. So to make it accessing the parameters, that is arguments passed to the main program to the subroutine, the frame pointer concept has been used. So here is a program. So we have written one program to demonstrate nesting of the subroutines. So just briefly, I'll explain this one. Look at the first program. So in the first program, I am passing the two parameters to the stack. So move parameter 1, move parameter to stack. Now look at the diagram on the right side. So parameter 1, parameter 2 is being put into the stack. Then I call the subroutine 1. So what is the next address after the call is a 2012, which will be saved. So look at the stack figure. 2012 is just saved here. Now the moment I say call, I come to the subroutine. What is the first thing I do? I am adopting the frame pointer concept. That is why I require a frame pointer to set up to a fixed place. So what you do? First, something will be there in the frame pointer. I don't want to spoil that. Copy the contents of the frame pointer to the stack. So look at that now. After the return address now, 2012 frame pointer will be pushed into the stack. Now set up the frame pointer. Copy the contents of stack pointer to the frame pointer. Now onwards, see, look at that frame pointer is fixed to this position for this subroutine. So in the whole of this subroutine, whenever I refer the frame pointer, it is always fixed address. It will not change. But whereas stack pointer keep changing still, because why? You are pushing some more things into the stack. So now this logic in this subroutine requires R0 to R3. So I don't want to spoil R0 R3. I'll push into the stack. So R0, R1, R2. Now stack pointer comes to this position. 4 registers, I pushed it. Now after that, I want to get the arguments in the subroutine, first subroutine, to start my implementing logic. How do I access the arguments? With reference to frame pointer, not with reference to stack pointer. 8 FP, first argument. 12 FP, second argument, I got into the register. Then I implement all my logics. Once I finish my logics, I want to return. Once I finish all my logics, I may require to call one more subroutine to implement another logic. So now I am setting up a call for another subroutine. So before setting up, what are the things I have to do? I have to push the arguments which is required to call the subroutine. Now assume that only one argument is required for calling the subroutine 2. So parameter 3, look at that, parameter 3. Now first stack frame is completed. Now the second stack frame starts. So what is the first element of the second stack frame? Parameter 3, I pushed it. Now call subroutine 2. What is the return address? 2164. 2164 is saved there. Now, so then you jump to the call subroutine 2. In the subroutine 2, what we do? First contents of frame pointer, we push to the stack. So frame pointer is pushed. Now copy the contents of frame pointer. So sorry, stack pointer to the frame pointer. And so there's one more change you have to do. So sorry for making a break here. Look at the first subroutine. It is not move FP, SP. It is move SP, FP. You please make a change here. There's one change here. Move SP, FP. So let's come back here. Move SP, FP. So then what will happen? You set up the frame pointer to the second stack frame. Now onwards, I can refer the argument called parameter 3 with reference to what? Frame pointer. Frame pointer plus 8 means what? I'll get the argument which has been passed to the second subroutine. Now again, second subroutine, before start using the logics, I'll push the registers R0, R1 into the stack. So R0, R1 minus SP. You can see that R0, R1 is being pushed. Now I'll get the argument which has been passed to the second subroutine by the first subroutine by reference to frame pointer 8 FP. Now you got into R0. Now implement all the logics. I'll finish everything. Now once I finish the subroutine, I want to go back to the first subroutine. I said you can use the stack to return the data answer of the second subroutine to the first one. How do you use it? Same place, the parameter 3, where it acts as an argument when you call the subroutine, the same place you can use it to return the answer also. So now what we do, assume that R1 contains the answer of the second subroutine. I am placing and the same place where argument was passed. You can just see that R1 8FP. Now answer of the second subroutine will be stored into the same place called parameter 3. Now I'll restore all whatever been pushed into the stack R1, R0. I just popped 2 registers, and then so whatever the frame pointer original value is there, I'll put it back to the frame pointer. Again, pop, one more pop operation we have done, and put to the frame pointer, then return. The moment I say return, so then what will happen? 2164 will be fetched, and the program continues from the move location of the first subroutine. So now once you are in the first subroutine, so what you do, you whatever the answer you got it from the second subroutine, you have to retrieve it. So where it is available? It's available so in the memory location. That is what it's there in the top of the stack. So move SP plus R2 means I am popping the top of the stack, which is nothing but parameter 3. Now stack point has got adjusted because why? You are popping once. So now where is the stack pointer? Now stack point is pointing to what? Top of the stack frame of the first subroutine. So now I'm concluding the first subroutine. What are the things I have to do it? So now answer, assuming that the answer of the first subroutine is there in the R3, I'm placing at the location called parameter 1, my answer. I'm just storing the answer of the first subroutine in the parameter 1, and then I am just popping out all the registers, whatever there in the stack, and also I'm popping out the frame pointer value now, and then return. When they say return, 2012 is fetched, and I'm continuing the program in the main program from the 2012. Now what all there in the still in the stack? Parameter 1 is there, parameter 2 is there. So now, so I can take the result from the top of the stack, move SP and result. I have not used the plus here. Look at there. I have not used plus here. So I've just taken the value from the top of the stack and stored in a value called result. Since I have not used the plus here, I have to adjust the stack pointer by 8. That means that because stack was pointing to the parameter 1, stack has to go to the old top of the stack. So 8, 4 plus 4, 8. I'm adding 8 to the stack pointer, and then the instruction continues. Like this, the stack frames are built one above the other whenever the nesting of the subroutines is done. So here stack is used to pass the arguments, to pass the result, to store the return address, and frame point is used to make the programmer easy to access the arguments which has been passed to the subroutines, and also to return the answers from subroutine to the main programs. So this completes so the unit 4. So we have covered all the concepts and all the solutions we have discussed. So go through their notes. For any doubt, you can always refer Hamisher as a reference book, which contains the explanation of this chapter. So we'll also share the videos. So for your further reference. Mohan, recording stop ಮಾಡ್ತೀರಾ?
Yes, sir. 1 minute.